today we're going to be performing the moment of inertia of a flywheel experiment. A flywheel is thought to be as a mechanical battery because it stores energy in the form of rotation. So Newton's first law, the law of inertia, states that an object in motion will remain in motion unless acted upon by an external force, or an object at rest will remain at rest unless acted on by an external force. So flywheels are typically heavy circular discs that are set in motion at first, and then they are let go to freely rotate. Now, once we want to extract that rotational energy at a later point, we're going to extract it through this flywheel, either by engaging it or by coupling it to another form of system. So a very typical example of a flywheel is one that sits between your engine and your transmission, so your gearbox. So whenever you press a clutch to disengage the gear, what happens is that flywheel continues to rotate, and when you want to when you move on to the next gear, it engages to the flywheel. What this does is this prevents excessive energy loss, so your engine doesn't have to start over from scratch. So this is typically how flywheels are used. They're used to store rotational energy through the means of inertia. So for this experiment, we're going to be using a simple mass hanger, a rope that we're going to coil, a 5 Newton mass, a stopwatch, and a vernier caliper to measure the dimensions of our flywheel. Because we want to compare our experimental values to our theoretical values, we're going to take the theoretical values from our measurements, and we're going to produce the experimental values through the mass hanger and the stopwatch. So there are 4 parts to this experiment. In the first part, we're going to rotate the entire system. So as you can see that there are 3 parts. There's the base, there's the outer ring, and then there's the inner ring. So in the first part, we're going to rotate the entire system, all 3 rings together. In the second part, we're going to remove the outer ring and rotate with the inner and the base. And then in the third part, we're going to rotate the outer ring and the base. And then in the final part, we're going to rotate just the base itself. We are going to attach the mass to its hanger, and we're going to attach the hanger to the string. According to our experimental guidelines, we're supposed to coil our string an arbitrary n number of times. I found that this string cannot be coiled more than 4 times, and that's the number of times I chose to coil it. You could choose 2 or 3, it doesn't really matter, but you have to keep note that your stopwatch has to stop when that number of rotations is complete. So I need to stop my stopwatch as soon as 4 rotations are complete. And as you can see, I'm trying to align the string to be perfectly in line with the horizontal. So I have to start my stopwatch as soon as I let go of the flywheel, and then I need to stop my stopwatch as soon as the mass drops. Once the mass drops, I need to continue counting the number of rotations that the flywheel completes, and when it stops, I need to estimate the angle at which it stopped, so in a fractional form. So we're gonna let go and start the stopwatch. So the same procedure is going to be repeated 3 more times with the various different combinations that I previously mentioned. You can take this measurement a few times in order to average out any forms of error, any errors in your data. So we're going to perform this experiment again, but this time without the outer ring. So go. there are bound to be some discrepancies in the data that you find, the experimental values that we find, and then the theoretical calculations. So take a closer look at this flywheel and try and anticipate what some of the sources of errors could be in this experiment.